All right, I want to give a very basic introduction to time complexity. So, time complexity is something that computer scientists think about so that they can compare algorithms regardless of how fast a particular computer is. It's not an issue of hardware or anything like that. It's in the abstract. How many operations does this algorithm need to perform to complete its task? That's the sort of question we're asking. And how many more operations does it take when the size of the problem gets bigger? So I just have a text document here. I've got a list of numbers. Suppose I'm trying to search for a particular number in this list of numbers. And I'm going to compare linear search and binary search. So linear search is where we just start reading through the list one number at a time and check to see if that number is the number we're looking for. So if I'm looking for the number 88, well, that's the worst case scenario because the 88 is at the very end and I'm going to start looking at the very beginning. So how many operations does it take? And I'm just going to include just checking as an operation. Well, I have to check each of the other numbers. Now, I didn't actually count up how many numbers I have here, but 1, 2, 3, 4, and so on until I get to the 88. If the size of my problem, the number of numbers that I have to search through, is 10, for example, then the worst case scenario is that I have to look at all 10, because I also have to check to see if this last number is my number, and then it is, and then I'm done. If the size of the list is 100 numbers, well, I have to check every single one of those. If it's 1,000, I have to check all 1,000. We would call this order n, or linear time. This is a linear algorithm. Order n, also known as big O of n, is a estimation. We're not going to worry about the details of the algorithm. We're not going to worry if it takes n plus 3 amount of time because there's 3 units of time involved in loading in our list of numbers. We don't worry about that. We're only going to worry about the largest exponent variable, which in this case is just going to be n to the first power. So that's the worst case for linear search. Now, what's the best case? You can probably imagine the best case is that we're searching for a number, maybe the number 1, and it appears right at the beginning of the list. So how long does it take us to search through a list of 10 items? In the best case, well, 1. How about 100? Well, still 1, because we just have to look at the very first number. How about 1,000? Still 1. So we would call this order 1, or constant time. Now again, if for some reason it actually took 5 units of time, it took 5 operations to find our number, we would actually still call this order 1, or constant time. We're being very vague intentionally to just get sort of the big picture view of these algorithms. Now, how about the expected case? Well, on average, if you don't know anything about your list, maybe it's random, or you just can't make any predictions about where your number is going to appear, maybe we're looking for something like the 90 here, then on average your number is going to be somewhere in the middle of the list. So we would expect it to take basically 5 steps, 5 comparisons on average for a problem of size 10. For 100, we might expect it to take 50. And for the 1,000, we might expect 500. Oh, I'm trying to get my thing to line up here. There we go. It might take 500 operations or calculations, or in this case, just checks, comparisons with the number. So what actually is our formula here? Well, you could very easily say that on average it takes n over 2 steps. However, this thing, big O notation, the order of an algorithm, which is written with a big capital O and then some variable, usually n, in parentheses with potentially, we'll see down here, it could be log base 2, could be n squared, any of those sorts of things. But it's not going to have a coefficient on it. We're not going to say n over 2 or 3n or anything like that. We're always just going to reduce it to this very simple single term, the largest term that is said to dominate the algorithm. And we're not going to worry about any of the further details. All right, so that's linear search. It's not terribly efficient, but it's sort of the simplest way to search through a list. And if we don't have any information about the ordering, well, this might be what we have to do. I paused my recording briefly there because I wanted to write down a different list. This list of numbers is in order. As you might imagine, if we have a list of numbers that's in order, we can find some value that we're looking for, or determine that it's not in the list, much faster than when it's not in order. Binary search is going to only operate on lists of numbers that are sorted. So here's my sorted list of numbers. What is binary search? It's what you might expect to do if you are looking for a particular value, what you would do as a person with an ordered list. You might look right in the middle and say, okay, is that middle number less than or greater than the number that I'm looking for? And if that middle number is less, you need to look on the greater half. And if it's greater, you need to look on the lesser half. It's basically I'm thinking of a number between 1 and 100. I'll tell you if your number is, your guess, or if my number is higher or lower after you give a guess. It's basically that game. So how long does it take to find a number on average when there are about 10 numbers in the list? Well, first we're going to check the middle number, or as close to it as we can, since there's an even number, right? We'll either have to check the number 5 item or the number 6 item. And then we'll look at the upper or lower half. Now, this is going to take, on average, about, what is it, 3? I think it's actually about 4. And I could calculate this if I was thinking about it a little bit harder, but that's all right. So it's about 4, and I'll justify that in a little bit. And you can also kind of just go through it, right? So cut 10 in half. It's down to 5. Okay, cut it in half again. Well, how do you cut 5 in half? And we're not allowed to cut, not allowed to go to 2.5 because we need to check each of these numbers separately. So we need to keep it with discrete whole numbers. So let's round up to 3. Cut it in half again. Again, we're not allowed to split numbers in half, so we'll just say, half of 3, the best we can do is 2. Split it in half, 1, and then we're finished. So I should have listed about 4 splits there to get down to our 1 number. For 100, it's a similar question. It's basically, how many times can you start with 100 and split the number in half before you get down to 1? But round up each time. Don't get rid of those halves because they're important because we need to check each and every number, right? So this is about 7, and for 1,000, it's about 10. I am being a little flaky with this for sure. And actually, let's look at it on our list here, although I don't remember how long this list is. So it looks like the 19 is right about in the center. If we start there, and I don't know exactly what number we're looking for, suppose we're looking for a lower number. Awesome. So our first split is going to only then further worry about these lower numbers. Let's see, what's in the middle of this one? It looks like the 8 is right in the middle. So maybe we'll compare our number to the 8 and look at what's, is our number higher or lower? Maybe we're looking for a number that's higher. Okay, so we might, and I'm just going to put the spaces in, we might have reduced the amount of numbers we have to search through down to these 3. Split it in half again. Now I'm going to compare to the middle number, which is going to be the 14 here. And that extra comparison is actually eliminating an extra number in my search, because if 14 is what I'm looking for, well, then I'm done. Maybe I'm looking for the number 10, so I need to go slightly lower and check to see, is it in my list when my list is just 9? Now, it's not. So I would say, okay, I haven't found it in my list, but I've reached a conclusion. So it took me 4 comparisons and splits to get down to my single number. As I mentioned, I did just say there 4 comparisons and splits, because I have to split the list in half. You might say, okay, well, 4 comparisons plus 4 splits, that would be 8 total operations. But in terms of the length of the list here, right, this is going to be n over 2. This is going to be n over 2. No, I'm sorry, not n over 2. I'm going to give away the answer here. This is going to be log base 2 of n is the number of comparisons we need to do and the number of splits we need to do. So in the end, you might say, oh, well, it took 2 times log base 2 of n operations, except, as usual, the big O notation is not going to worry about coefficients. So we're simply going to say that it takes order log base 2 of n, or even just order log n is typically what we would say. Now, why log base 2 of all things? Well, what is the log base 2 of a number? And let's actually use a number that has a nice log base 2. Let's use 8. So log base 2 of 8, the answer is 3, but how do I arrive at that 3? Log base 2 of a number is basically asking the question, 2 raised to what power gives me the number in the parentheses? And the answer here is 3. So 2 cubed gives me 8. And you can sort of calculate this out long ways for any particular number. Let's say 56. I'm going to estimate what's the log base 2 of 56. And what I could do is I could say, okay, well, 2 to the first power is 2. And then the second power, 4, 8, 16, 32, 64. Uh-oh, I went too high. All right, so it's somewhere between, what did I say here, 2 to the 5th. It's somewhere between 2 to the 5th and 2 to the 6th. Now, I don't know exactly what it is, and from here, I can't do the mental math, but, you know, I could just estimate it as 2.5, or I could just say it's between 2 to the 5th and 2 to the 6th. Okay, so that's just a little logarithm reminder there. Let's look at the rest of our binary search. So in the best case, well, in the best case, if we're looking at the middle number, well, the middle number is just the one that we're always looking at, and we'll just find it immediately because that's the first number that we check. And it's in order 1 constant time. Now, with the big O notation, you never really pay attention to the best case. We're either concerned about the worst case or the expected case, as you might imagine. The expected case is just on average what's going to happen. And on average, we're going to need to do something close to the worst case, actually. But the worst case is actually really not bad for binary search. Log base 2 of n, which is, by the way, reminder, the size of our whole list, is actually a very low number, even compared to n. And if we go to the Wikipedia time complexity page, they have a nice graph to show us these. All right, so right here on the right side of the page here, they have this time complexity graph. And we see right in the middle is the linear time, the order n. And then everything below it is in these cool purples and blue colors. Log base 2 of n is the dark blue, not the purple, which is constant time, order 1. And then square root n is also there. And then we see some of the slower times. And on this graph, I mean, based on how it's scaled and sized, the slower ones are considerably slower. It takes much more time with n squared, and even n times log base 2 of n. N factorial is really terrible over here, 2 to the n. Those are the ones that we're trying to avoid. And sometimes, you know, the fastest algorithm does have to be n log 2 of n. There's actually mathematical proofs for certain algorithms and things like that. And this is something that computer scientists study. It's something that a software engineer certainly needs to be knowledgeable about, but it's not necessarily the most practical thing because there are hardware concerns, there are implementation details that will certainly change the actual runtime of an algorithm. But it's still important to have this big picture analysis of how is the algorithm in general, regardless of the particular programming language or hardware that we're using to execute it. So I hope that helped as just a little introduction to time complexity and big O notation.